Let's look at a new example where we will calculate all the different things about this given function on the given interval. So we're going to get the intervals of increasing and decreasing, the absolute and local extrema, the intervals of concave up and down, and then we'll sketch the graph. So the absolute extrema, that comes from 3.1. So all we need for right now is the equation of this function. So it's y equals x plus cosine x. We need to take the first derivative. That will be 1 minus sine x. Again, we want to figure out where the first derivative is positive and where it's negative, and what's helpful for that is to set it equal to 0 and use test points. If I add sine x to both sides, I get 1 equals sine x. Where in the interval 0 to 2 pi is sine x equal to 1? Well, again, we can remind ourselves with a quick graph of the sine function. The only place where sine of x is equal to 1 in the interval 0 to 2 pi is at pi over 2. That's going to be our dividing point for the first derivative. I'm going to pick test points that are relatively easy to work with. Again, I cannot pick 0 because we have to pick a point where we know the derivative exists so that when we plug it in, it'll make sense. Alright, so I'm going to use x equals pi over 4, and for the right side, I'll just pick x equals pi. Again, we're plugging these test points into the first derivative function to see whether we get a positive or a negative. So if I do that, I get that y prime of pi over 4 is 1 minus sine of pi over 4. So it's 1 minus root 2 over 2. I could use my calculator to figure out whether or not this is positive or negative, but I know that square root of 2 over 2 is some number that's less than 1. So if I have 1 minus a number that's less than 1, then I know I'm going to end up with a positive number. I don't care what the number is right now, I'm just trying to check positive or negative. Similarly, for y prime of pi, I'm going to have 1 minus sine of pi. That's 1 minus 0, which is 1, which is positive. Okay, so it looks like this function is going to increase all the way. So our intervals of increasing and decreasing, well, we're going to have just one interval and it's going to be all increasing. So the increasing interval will just be 0 to 2 pi. And I'm making it an open interval again because what happens at the endpoints is not clear. Okay. Absolute and local extrema. Okay, well, let's think about local extrema for a second. That's supposed to happen where the first derivative changes from positive to negative or from negative to positive. And we don't have that happening here, which means we don't have any local extrema. But we're on a closed interval, and that means we can figure out the absolute extrema. we have a continuous function on a closed interval, and it's differentiable on this open interval. That means by the extreme value theorem that we have an absolute maximum and an absolute minimum. So since we don't have any local extrema to try to plug in, the absolute min and absolute max will probably happen at the endpoints. Those are the only places where that will be possible. So we take our endpoints and plug them into the original function. Y of 0 is 0 plus cosine of 0, which is 1. And y of 2 pi is 2 pi plus cosine of 2 pi, which is 2 pi plus 1. We have then that our absolute max is 2 pi plus 1, and it happens at x equals 2 pi. And then our absolute minimum is 1, and it happens at x equals 0. All right, what about intervals of concave up, concave down? For that, we need to take the second derivative. So y double prime, again looking at my first derivative, here's my first derivative, 1 minus sine x. When I take the derivative of that, that will give me the second derivative. So derivative of 1 minus sine x is 0 minus cosine x. To find the intervals of concave up and down, as we mentioned, we need to figure out where is the second derivative positive, where is it negative. And again, to help us do that, it's good to set this quantity equal to 0 and solve. We're in the interval 0 to 2 pi. So we ask ourselves, for what values of x in 0 to 2 pi is cosine of x equal to 0? I think I need a cosine graph to help remind me. So let's see, we have this. Okay, so 2 pi. Here's pi. These are the points I care about. This is pi over 2 and 3 pi over 2. So I have x equals pi over 2 and x equals 3 pi over 2. What I need to do at this point is determine the concavity on either side of pi over 2 and either side of 3 pi over 2. Test points. Let's say x equal pi over 4, x equal pi, and I can't pick 2 pi, so maybe I'll pick 7 pi over 4. Pause the video, figure out the test points, determine the signs of the second derivative in each of these 3 indicated regions. Remember that y double prime is actually the function negative cosine x. So you should have gotten negative, positive, negative. What we have is a situation where the function is increasing to the left of pi over 2 and concave down. Then we have still increasing but concave up and then changing to concave down later. So changing to concave down sometime after that. Let's use this information to try to graph this function. Okay, we need some y values. Well, let's see. We have a couple of y values. We have that y of 0 is 1. We have the point 0, 1. And then we also have this other point when y is 2 pi. Sorry, when x is 2 pi, y is 2 pi plus 1. Alright, so let's say 2 pi is right here. And this is 1. 2 pi plus 1, that's a little more than 7. So 1, 2, 3, 4, 5, 6, 7. Alright, so we have these 2 points. What are our points of interest? Well, we have pi over 2 and 3 pi over 2 on the x-axis. That's where interesting things happen. That means we should probably figure out the function values at those points. So we have pi over 2 comma pi over 2, because cosine of pi over 2 is 0. And then y of 3 pi over 2 is 3 pi over 2 plus cosine of 3 pi over 2, which is 3 pi over 2. So we have the point 3 pi over 2, 3 pi over 2. And let's see, 3 pi over 2 is approximately, it's about 4.5. So let's see, 1, 2, 3, 4.5 is about there. And then for the point pi over 2 to pi over 2, pi over 2 is about 1.5. So I have this here. Okay. So on the interval 0 to 2 pi, what's happening? The function is always increasing. So what we need to focus on is the concavity. From 0 to pi over 2, we have concave down, which means it'll look something like this. And it's important to notice that pi over 2 is where the derivative is equal to 0. So I should have something flat happening, a flat tangent line happening at x equals pi over 2. Between pi over 2 and 3 pi over 2, we have concave up. Function is still increasing. And then it changes to concave down after 3 pi over 2. So we get something like that. Remember, since our sign changed for our second derivative, we have an inflection point. Not that the problem's asking for that, but it's important to remember that. There's also another inflection point, which is at x equals pi over 2.